everyone, this is your Air Pollution Part 2 lecture. Make sure that you have already watched Part 1 prior to watching the second part. Now that we've had an introduction to different types of pollutants and their effect on the environment and human health, we're going to start with going through some specific pollutant formation. And to be able to do that, we need to know the difference between primary and secondary pollutants. So first of all, your primary pollutants are going to be pollutants that are emitted directly into the atmosphere. So for example, if the chemical is coming out of the tailpipe of a car or out of a smokestack at an industrial facility, chemicals that are primary pollutants would include carbon monoxide, carbon dioxide, sulfur dioxide, and your NOx chemicals or your nitrogen oxides, such as nitrogen dioxide and nitric oxide. These primary pollutants can then undergo further chemical reactions within the atmosphere, and they can form secondary pollutants. So secondary pollutants are chemicals that are not directly emitted. They come from the primary pollutants having chemical reactions in the atmosphere, usually through the exposure to sunlight, water, oxygen, or other compounds within the atmosphere that they react with. These secondary pollutants can include ozone, which is abbreviated O3, sulfate, SO4, and nitrate, NO3. You should know what pollutants are primary pollutants and what pollutants are secondary pollutants, so make sure you have that in your notes. Sulfate and nitrate are the main components that are actually going to contribute to acid deposition or acid rain, and we will be hearing more about acid rain in our next lecture. So to recap your primary and secondary pollutants, your primary pollutants are going to come from direct sources. So if you notice the car, the factories, we also have the ship and also the volcano, those pollutants are emitted directly out of those sources. So notice that it includes a couple pollutants on the list there, such as the nitrogen dioxide, the nitric oxide, and the VOCs. These primary pollutants then will react within the atmosphere, and within the atmosphere we have the oxygen compound ozone created, or O3, and other pollutants such as PANs. The next thing that we need to discuss is the creation of photochemical smog. But first of all, what you should know is that photochemical smog is formed when nitrogen oxides, or your NOx chemicals, and VOCs, or your volatile organic chemicals, react with heat and sunlight. And what will happen from that reaction is pollutants will be produced ultimately in the form of a brown haze. The everyday term for this is just smog. We don't usually add the photochemical in front of it, but the proper term for environmental science class is photochemical smog, so make sure you know the whole thing. Nitrogen oxides are often produced very early in the morning. This is often due to rush hour, just a lot of cars on the road. The emissions from these vehicles are going to lead to the reactions that take place to create the smog. And then ozone levels, or O3, they are going to peak later in the afternoon. And the next thing we're going to look at is the reactions that take place that cause the ozone to peak in the afternoon. One additional thing, though, that we need to know about ozone is that ozone levels are often higher in the summer because ozone is created due to a reaction of sunlight taking place in the atmosphere with oxygen, or O2. So if you take a look at our picture on the right, you can see that the sun's rays are coming in and striking the oxygen, O2, and then that chemical is going to break apart. So we can see it split into two different oxygens. And then what will happen is that single oxygen is a little unstable. So it's going to try to seek out chemicals it can bind with to make it more stable. And often what that is going to be is another O2. And so it will join up with the O2, and when these guys get together, they will form O3. Okay, so we're going to take a look at the steps of the photochemical smog formation reaction. I'm going to walk through it with you in words here so you can take some notes down, and then what we'll do is take a look at a picture walkthrough of these same reactions to recap them. So what will happen with photochemical smog is your nitrogen dioxide, or NO2, are going to break down once they're released into the atmosphere, again, commonly by motor vehicles. Sunlight is going to react with them, and they are going to form NO, or nitric oxide, and an oxygen radical, so a single O. So NO2 breaks apart, and it forms NO and O. That single O radical is then going to go react with oxygen to form ozone, similarly to the reaction we just looked at. Then what will happen is the NO, the nitric oxide that was released from the first step, is going to react with the ozone, and that was formed in the second step. So NO reacts with O3, and they are going to create two chemicals, and that is NO2, or nitrogen dioxide again, and also oxygen gas. That nitrogen dioxide that's created again is then going to react again through the first step. So let's go ahead and recap this reaction again using pictures. So you can see we have NO2, nitrogen dioxide, that's been released into the atmosphere. Again, this is common in early mornings as everyone is driving to work because it's coming out of the tailpipes of their cars. We are going to see that NO2 split in to NO, nitric oxide, and an oxygen radical. And remember what we said earlier, that oxygen radical is a little unstable, so it wants to go join up with something to stabilize a little more. So that oxygen radical goes and finds an oxygen, or an O2, and it is going to create ozone, or O3. And what we need to remember about ozone is it tends to peak in the afternoon as these reactions have been taking place, and that it also is going to be higher in the summer because the sun helps encourage all these reactions. What will then happen with ozone is it is going to react to the NO that was released earlier. So we can see in the bottom picture down here, we have our ozone reacting with nitric oxide, or NO, and they will separate into atmospheric oxygen, or O2, and NO2, and then that NO2 can actually go back and do this reaction at the top all over again. A bit of a problem though can occur when VOCs, or volatile organic chemicals, are present. If they are present, we are going to get a slightly different reaction taking place. So if we take a look at our picture over here on the right, we can see that the NO2 is having its normal reaction across the top. So our normal reaction that's taking place has our NO2 breaking into NO and an oxygen radical, that oxygen radical joining up with the O2 to form ozone. When VOCs are present though, we get kind of the reaction hijacked in a way. So what will happen instead is the NO is going to come down here and react with VOCs instead of going through the ozone formation we see at the top. And when the VOCs are reacting with NO, we get photochemical oxidants. Well, the problem is if there are already some ozone molecules in the atmosphere, those combined with photochemical oxidants can lead to the smoggy haze that we mentioned earlier. This also means that because ozone is not reacting with NO, like we talked about earlier, we are going to have ozone build up in the atmosphere instead of recreating the nitrogen dioxide, or NO2, and oxygen that is released back into the atmosphere. So that buildup of ozone added to the photochemical oxidants are going to lead to smog formation. There are also a variety of environmental factors that can play into how much smog affects a certain area. For example, if you have a city that is found in a valley or is located between a coastline and a mountain range, we tend to have smog be a little bit worse in those types of cities as opposed to cities that are found on more open topography or open land, such as a plain. Weather changes can also influence smog accumulation. So we're going to talk about thermal inversions next, which is one way that weather can cause some severe smog problems. All right, so a little recap on the temperatures in the atmosphere. Closer to the Earth's surface, temperatures tend to be a little warmer in the atmosphere. And then as you go further away from the Earth, you tend to get cooler and cooler temperatures going further up into higher altitudes. That warmer air is usually, again, very close to the Earth in lower altitudes. But sometimes we can have a kind of switching of those temperatures, creating what's known as a thermal inversion. And the problem with these thermal inversions is they can trap very dangerous emissions or pollution beneath them. So if you take a look at the left, you can see our normal conditions. Again, warm air closest to the Earth getting cooler as you go into higher altitudes. With a thermal inversion though, instead of warm air being closest to the Earth, it's actually air that's a little bit colder, and then a warm air layer gets formed above that. Well, what happens is that warm air basically traps pollution within that colder bottom air layer. So if you look at the picture on the right, you can see in that thermal inversion, the brown smoggy cloud. So that is the pollution being trapped in the inverted air that is cold and closer to the Earth's surface by the warmer air that is now above it, where it would not normally be. Thermal inversions have caused a few major disasters throughout human history, one of the most famous being the Great Smog that occurred in 1952 in London. There was a thermal inversion that took place, and basically because Londoners had been burning so much coal because it was very cold in December, the coal pollution in the atmosphere became trapped close to the ground due to that thermal inversion. And there are up to about 12,000 deaths that were attributed to this particular event due to respiratory illnesses and complications because of the pollution. All right, the last thing we need to discuss for this particular lecture is a couple ways we can reduce smog. Some of them are just kind of common sense. For example, lowering car emissions, or just having less cars in general in an area. So we need to help lower those emissions to reduce the smog that's created through the nitrogen oxides and the VOCs released into the atmosphere undergoing the photochemical smog reactions. The car emissions are a big reason why a lot of larger cities have a lot of smog. LA is a perfect example of this, as well as some other major cities in Europe, like London as well. We can also try to reduce some of the precursor chemicals that form the secondary pollutants, such as ozone. We can't really target the problematic secondary pollutants because they're an atmospheric reaction, but we can try to stop the primary pollutants that lead to their creation. Thank you for watching the Air Pollution Part 2 notes.